Hello students, good morning to all of you. Student, in previous class we learned about the concept of mobility of charge carrier and the current density. Now we continued with the same topic, and next topic we have in current electricity is Ohm's law. It is most important law related to the simple circuit, which gives us an idea about the different kind of material on the behalf of applied potential difference. Okay, so according to this law, the potential difference applied across the end of a conductor of any cross-sectional area is directly proportional to the current flows through the conductor. That means V is directly proportional to I, or you can also say that the I is directly proportional to V. Okay, when we taken out this proportional to sign, we get a result that R into I. Okay, here this R is proportional to constant and known as resistance of used conductor or material. Resistance of material of conductor. Resistance of conductor. Okay. Now from here you will get this R is in the ratio of applied potential difference to the current flows through the conductor. Okay, and from here this R is directly proportional to V, and this R is inversely proportional to I. Both the things are linked with the here the degree of potential difference, and this is seen, and here also the degree of current and the resistor are seen. So we get the graph drawn for some values of the voltage and current such that if we find that the potential is 0, we get the result for the current is also 0. And as the potential will increase, suppose that the potential is increased 0.5, we get the current increase by 1. And when the potential increased again by 5, we get the current increase by 2. And similarly, as we increase the voltage by every different observation by 0.5 volt, we get the current increase by 1 unit. And now is 4. When we draw the graph for the observed value, here x-axis is defined for the current and y-axis is defined for the potential difference. Okay, so the values are start from 0, 1, 2, 3 and 4, 0.5, 0.5, 1, 1.5, 2, 2.5 and 3. Okay, when we draw the graph, we get the initial point is here. For the 1 potential, we get this result is here, and when we draw for potential 1.5, we get the point is here, and similarly for the next value of potential we get this result is here. When we join these all points, we get a straight line. We get a straight line like that, and this line is inclined on the current axis by an angle. So we can say that the inclined line having a slope, and that slope gives us the value of r by calculating any 2 points on this line by using the relation the slope r is equal to del v upon del I. Del v upon del I is r. Just find from here. If we take the 2 points, let's say point A and this is point B, and a perpendicular drop is dropped here till the point C, then you will easily observe this, that this value is del V and this value is del I. Okay, so we observed for the conductor the ratio of the potential difference and the current is always a straight line, and it is also observed that as the temperature will increase, we observe the resistance of the conductor is also increased. Okay, just write the statement of Ohm's law. According to this law, when the physical conditions like temperature and pressure kept constant, then the current flowing through the conductor of any cross-sectional area, is directly proportional to the applied potential difference across the end of the conductor. Now student, we understood about this coefficient of the material named as resistor. Okay, so you can easily define that resistor or resistance of a conductor or material wire is in the ratio of resistance of conductor is defined in the ratio of applied potential difference to current flows through the wire. Okay. What is the cause of resistance? Just we understood this. Cause of resistance. Okay. As in the previous class you learned, the conductor have many free electrons in it. Which are in random motion. Okay, because these electrons are in random motion. So when the end of the conductor is applied across a battery, then let's say the electron from the negative terminal E is try to move toward the positive terminal of the end of conductor to P. When it is moving from Q to P, there are, except of this, other free electrons are trying to obstruct the path of this electron and want to reach before it towards the end P. So because this electron is moving influence of the applied or set up electric field across the end of conductor is obstructed by these free electrons, and due to the obstruction the metal or the conductor is heated up due to the many several collision between the free electrons and the electron moving towards Q to P. Okay, so these obstruction offered by the conductor when an electron is moving from Q to P is known as the resistance of the conductor. Okay, so you can also say that the obstruction offered, resistance of a conductor, obstacle offered in the flow of charge obstruction offered by conductor in the flow of current across its end. Across its ends. Okay, due to collision between free electrons in the conductor. Okay, now SI unit of resistance is ohm, and it is denoted by the Greek symbol this. Okay, now it is basically is volt per ampere. Okay, derived from the unit of potential difference and the unit of current. The dimensional formula for resistance is ML2 T minus 3 A minus 2. This is the dimensional formula for the current, for the resistance. Okay. Now next we have or specific resistance. Okay, specific resistance. So suppose we have a conductor of length L and any area of cross section, let's say A, and it has number density of free electron N, due to which it offer the obstruction across the moving charge towards P, or you can say Q to P. Okay, it is observed that the resistance of the conductor is directly proportional to length. The resistance of conductor is inversely proportional to the area of cross section, and when we use the two laws, we get the resistance is directly proportional to the ratio of the length and the area. When we taken out this proportional to sign, we get this result is equal to R rho L upon A. Here this rho is specific resistance, or you can say resistivity. Resistivity of conductor. Okay, resistivity of conductor. Student, here the resistivity of a conductor is material characteristic. Material characteristic. Okay, which means it does not depend on the geometry of the conductor. Okay, now we taken out the formula for the resistivity, that rho is equal to R A upon L. Okay, now just understood from here that if ratio of the area or length is 1 unit, that is, if area is 1 meter square and length is 1 meter, then this will become 1 meter, or you can say 1 unit or unity. Okay, then we observe here the resistivity of a conductor is directly equal to the resistance offered by the conductor. Okay, now you can write the definition for the specific resistance. Specific resistance or you can say resistivity of a conductor or you can say material wire which is used in our circuit. Okay, conductor is directly or you can say is equal to the resistance offered by conductor when the ratio of area of cross section to area of cross section to length of conductor is unity, or you can say unit. This is the definition of the specific resistance of a conductor. And here you can also use one meter or unit. We have a formula for the specific resistance, that this specific resistance is equal to M upon N E square tau. Okay, here this M is the mass of electron, N is number density of electron in the given conductor, E is charge on electron. Here we get that this resistivity is inversely proportional to the time of collision. Okay, and here the temperature is directly proportional to the relaxation time of collision, which means as the temperature increase, 1 minute. Temperature is inversely proportional to relaxation time of collision, which means as the temperature of the conductor increased, the time of collision will decrease. As the time of collision will decrease across between the two consecutive collision of electron with the free electron, we get the resistivity will increase. Then from here you will get the resistivity of a conductor is directly proportional to the temperature, which means as the temperature will increase, the resistivity is increase for the metal or conductor. We discuss it after. Now we derive the formula for the Ohm's law. Then we discuss about all these things one by one on the effect of temperature. Okay students, derivation for Ohm's law. As we discussed in the previous lectures, that if we have a conductor of length L and area of cross section A, because it has many free electrons, and if a potential applied across a battery by a battery across the end of the conductor from P to Q of potential difference V volt, then a current flows across the end PQ of a conductor, which is given by I is equal to NEA VD. Okay, where N is number density of electron, E is charge on electron, A is area of cross section of the conductor, and Vd is drift velocity of electron from by which the electron is moves from and Q to and P. Okay, now here let's say this is equation first. We know that the drift velocity is given by E capital E upon m tau. Here E is charge on electron, capital E is electric field applied, m is mass of electron, and tau is the relaxation time between the two collisions. By using this, and we have the value of electric field is V upon L, where V is potential difference and L is length of conductor. Okay, now this is, let's say, equation third. Therefore, from second and third equation we get the drift velocity Vd is equal to E m V L into tau. This is equation 4. Therefore, from equation first and equation 4 we get I is equal to NE A, and here is in place of Vd E m V L tau. On solving this, NE square m tau NE square A tau V okay, just write in such a way, and V. Okay, now the microscopic things like number density, electron, mass of electron with area and length, and the relaxation time taken in a bracket except of V. Now we calculate from here V upon I. For calculating this I substitute to the denominator of V, and all things are substitute here. We get here m L N E square A E square A tau. Okay, now after that this we have the value of resistance m n E square tau taken in one bracket and L upon A here. This is your equation 5th. Okay, now and here we have used that V upon I is equal to resistance of the conductor. Now here R is equal to rho L upon A, where rho is equal to m upon n E square tau, which we calculate just before it. Okay, now mm, 1 minute, 1 minute, 1 minute, 1 minute. Okay, this is equation 6. Now by this is equation 5, this is 6, and this is equation 7. Now by equation 5th and 7th we get V upon I is equal to R. Therefore this V is equal to R into I, and we get I is proportional, V is proportional to I. This is the required relation for Ohm's law. Okay, note it. Thank you.